I remember vividly watching, a math teacher I really respect, delivering a session which was very hard, and a student said to me, "Sir, I'm lost," and he responded, "You're at Rushcliffe School, on Rushcliffe Lane, and I hope you find your way home," and then walked away. And in his classroom, there's no "I don't get it," there's no "I'm lost," right? You apply yourself, and then you ask me a very specific question about, "Sir, actually, I know we're supposed to be looking for locations in memory, but I don't understand what memory is." I can accept that question. I don't get it, I'm not even going to respond, I'm afraid. Okay, so, this is assembly language. Now, first of all, do we all know how to split screen? Because split screening will be very, very important for this session. So, the way we split screen is we grab the tab like this, we drag it all the way over to the side, and then we let go. And then we click the window that we want. Now, this is very important because this is a tough old lesson. And what I need you to do is I need you to be able to see the question, and I also need you to be able to see the simulator. If you have not done this, I'm going to give you 15 seconds to do that now. If you've not split screen now for me, please. I know some of you haven't split screened, been walking around. Split screen now for me, please. 5 more seconds. Remember, we're grabbing the tab, dragging it to the middle center, and then we're letting go, and now we can see both at the same time. Okay, now we can see all of our information all in one place. Now what we can do is we're just going to read this. Below Python code, I'm assigning a variable, assigning another variable, adding those two variables together. We can discuss about how correct that code is, but fundamentally, we all know how to assign variables. We all know how to do something describable as a plus, and we all know how to print output. Now, what I'm trying to convince you of is that in assembly code, when you're looking right into the heart of the computer, is that it's not that much different, and it's not that much harder. Okay, so we go from 3 lines to 5 lines. No reason to feel sorry for ourselves. 5 lines is not that many lines, yeah? So we go from 3 lines to 5 lines. The first thing we're going to need to do is we're going to need to run this. Now, I'm not going to ask you to predict. Why am I not going to ask you to predict? Celine, why am I not going to ask you to predict this assembly code? Because I have told you what it does. What does it do?
Print number and add it.
So it assigns 2 variables, and then it...
The add will be adding both the 3 of assign number 1 and number 2.
Perfect. So I assign the variables, I add them, and then I output that answer. Exactly right. So all I need to do now is I need to run it. So when I click submit, well, it does something. I can either click submit or assemble into RAM. And it did something strange. Did anybody see what it actually did? Does anybody need me to go again? Let's go one more time. So let's refresh this, and then I'm going to drag this. Now look very, very carefully at what changes. Very carefully. Abdullah, what changed?
The content of the summer.
Yeah, it did. Lovely. So one by one, these instructions were assembled into RAM. Here, this was just lines on a page. This might have been in secondary storage, but now it gets assembled into primary memory. We lost 5 memory locations to make the 5 instructions that run my program. Yes, please.
So, where do those values come from that are put in there? Where are they coming from?
So I love that question, and your question is related to why does the word input in Python mean input? Now, this might look very different, but believe it or not, it's the same. And the reason it's the same is because computers only speak number, right? And not only do they only speak number, we could make it even more complicated and try and do that in binary, but I wouldn't do that to you. So computers only speak number. So this is we call it machine code. This is the machine code for all of these instructions. Now, let's see, based on that fact alone, whether we can decode this. So, Dennis, what is the first one likely to mean? 901.
First numbers represents instruction register, and the second one represents the address of the.
You've pitched that super high for me, Dennis. Literally, all I want is you to say in words that we might all understand what 901 might mean. Bearing in mind the computer can only represent instructions as numbers. What does that first line do? Simple as you can. Oh, there we go, Celine, thank you. It's input, isn't it? 901 is input. It's not a trick question. 901 is input. Now, what does 320 do? Bit harder, but again, we can look across for a Q. STA20.
Store 20?
Okay, let's put that on the shelf and exactly what that means. So store 20, yes, but let's put that on the shelf exactly what that means. But again, that makes sense because we're representing the variable, isn't it? We're assigning a variable, so somehow this is doing the same thing. And then we're doing the same thing, input, we're doing input again with the 901. 120?
That's so 1 is, I guess, the code for add, and then 20 is the location. So add whatever is in the accumulator to the value at the register.
Okay, you've gone very high level. So, but what I'm going to take from that is 1 is add,
Yeah.
and 20 is a place where the thing I want to add lives. And we don't see that here, but the same thing's happening. We just, in high level code, we're allowed to give locations names. And the name here is num1, the name is num2. But actually, in assembly code, we don't do names. We're saying exactly where it is. Okay, listen, a lot of words. Now it's time to enjoy some pretty moving images. So watch very carefully. What just happened? What just happened?
So
What
the,
just happened?
Yeah, so the program progressed and it retrieved the address. Sorry, yeah, the address at 0.
Okay, I'm just going to pause you there. Nabil, how might it have known to go to 0? Because in computers, everything is very, very explicit. It's not like you where I say, Nabil, can you get me a sandwich? And Nabil walks out the door and he goes, I could go to Greg's, I could go to Subway, I could go to Sainsbury's. Computer's not like that, right? If it goes to 0, it's because it's going to do that every time. How does it know to go to 0 for that first?
It's the start, it's the start number, it's the first slot.
So that would be a nice answer, but I'm going to give you a clue. It's something to do with the program counter.
The program was 0 before.
Right, so before we start the next instruction, the program counter points to that next instruction, right? And actually, what happened to the program counter when I clicked run just then?
It increased by 1.
It went one forwards, pointing at the next location. Very good. So it's asked me for an input, so it's actually executed 901. Let's see what happens when I put in. Somebody give me a number between 0 and 10. Christian, please. 7. So let's put 7 in just there. Click enter. Interesting, 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 interesting. Nabil, your job now is you are the counter of the program counter. Yeah? Okay, what happens to the program counter, Nabil?
Counted, so it was at 1 before and now
Yep.
it's at 3.
And did you notice the red thing move along?
Yeah, because it was going to that specific.
Exactly right. And then we've executed this instruction. We didn't need to pause there, right? It said 320, that's store. So what's stored now at 20? The location 20? 7, which is exactly what we want. Okay, let's put another number in. Before we execute this now, counter the program counter, what will be the next instruction executed by this computer before I click enter? So tell me what's going to be next.
To add 1 to the start,
902.
So we've got a disagreement. We've got add 1 and we've got 902. I mean, you're both in a sense right. We are currently doing this one. No, sorry, we're currently doing this one. The next one will be this one. So
120.
yeah, absolutely. And then let's click enter and let's see what it does. And this will hopefully crash. There we go. Oh, halted, sorry, technical terminology. It's halted. Okay, what is the value in the accumulator? What value is outputted? What is the relevance of the number 12? It's my inputs added together. Guys, you just saw the way your computer actually runs your instructions. It literally looks a little something like this. Okay, architectures vary and you don't have 100 locations in your RAM. You're going to have some many billions of locations in your RAM. But this is the basic idea. I'm just going to drop out of that was the emotion that I need. Liam,
I
you say
just
what
got it.
happened.
I just got it. I got what the figures mean. Sorry.
I hope that experience to happen to everybody in this room by the end of today. And I'm just going to drop out of roll.
Didn't need that visible. Though.
No, that's why we do this. That's why we do this. I'm just going to drop out of roll for a second there. I would generally, you know how I have my thing about reading questions 3 times? I would not take any issues from any student until they had run this 3 times and watched it intently. Yeah? That, by the time we're having this conversation, I know that every student has watched the pretty pictures. And if they've not, then what they've done is they've opted out. Right? Because there is no minimum, you don't need any level on SATs to watch pretty pictures. Right? That's all I needed them to do, just watch some pretty pictures. And I wanted them to do that 3 times. And you know what? This will work really well for some of your with some of your students with the most complex needs. Right? That kind of barely verbal autistic student, this might really work. Right?
They've actually built these like in Minecraft.
Oh, really?
It's hilarious.
People get obsessed with it. I went through a phase where I would refuse to write any Python code and I wrote everything in assembly on a little non-computer. I'm not joking.
This is probably a really random high-level question. I
Yeah.
know it wouldn't impact a modern CPU because modern
Yeah.
CPU has, I think we calculated, didn't we, had like 18 pentillion kind of storage locations. But say your instructions fill every storage location. What would happen in terms of trying to store values?
So now you've got this wonderful conversation. Anybody know what this is a topic of an entire lesson? What's that lesson called? What's the lesson? It's sometimes part of the lesson on RAM, or sometimes it's its own lesson.
So is it stored
Computer
virtually
modules.
or?
Begins with a V.
Error codes.
Begins with there we go. Virtual memory.
Yeah.
So what will
Well,
generally
that might be
happen
better.
on modern computers
Yeah.
is they will make use of secondary storage as if it was RAM.
Right.
Now imagine how horrific that is.
Yeah.
Because everything, like the instructions even to execute, well, first of all, you're going to use some primary memory telling the computer to use secondary memory as primary memory. That's horrific already. Then anything that's going to go through this has to pass through that. It's going to be bad.
Yeah.
It's going to be really bad. Its only purpose is to not crash your computer.
Yeah.
And maybe you'll get away with it. Maybe you'll get away with it because you've got solid state drives, which are fast, and you're just going to use it for OS functions, right? But it's going to be bad.
Yeah.
Any more for any more? So yeah, this is a lovely way of motivating virtual memory. You know, with what you've just done. Again, how many lessons do you think I'm going to do this for? It's going to have to be a few.
That's what I was going to say, probably. But
We're not really going to understand it at the end of 1. At the end of 2, you might have enough to move on. Yeah. So I would probably split the worksheet I gave you over 2 lessons.
I mean, I've got a degree in computer science and I've only just gone, oh, I get it.
There you go. And they won't understand von Neumann architecture in its entirety from this lesson. But what they might do is go, oh, registers are real things, they're real places, and RAM is a real place, and what's going on is not very abstract at all. It's a little gremlin moving these little codes around, and that's literally all it is.
Little gremlin.
Yeah, it's just a little, it's just a little whatever, and it just moves instructions around, and that's all it is. And that's what makes it so remarkable that this has caused the digital revolution, right? It's just a little, arguably the greatest genius of the 20th century, John von Neumann.
Like, what even went through his head thinking that this would be a thing?
Well, he was already, I think, suffering from dementia at that point. So, I mean, he had various plans, including bombing the Russians, and he was one of. It's a very interesting story. There's a book called I can't remember its name, but it's about his descent into insanity because the White House was still listening to his ideas at that point, and he was losing it, good and proper. So, but most of the time when he was fully there, he was a genius, true genius, like very few others. And he was trying to imitate the mind.
And are
do it
modern
rigorously.
CPUs still based on this kind of architecture?
Get a little bit more crossover now with Harvard and things like that. But yes, ARM is still von Neumann, right? And everyone gets very excited about ARM, except people who own ARM computers who think they're terrible. Yeah, it's all von Neumann. It's all von Neumann. And listen, I could talk for an hour about this, but I'm gonna move us on ever so slightly. So let's pause this there. 16 minutes.